All right, here we are now for Math Tidbits number 5. And that is on vector product using components. Now, this is going to be a lot more detailed of a discussion of the vector or cross product than we had before, necessarily, because before we did something essentially qualitative. We gave, for the case, let's say, of vectors A and B with angle theta between. We gave the cross product magnitude as AB sine theta. So we did do that much in terms of quantitative things. We also talked about the direction of the cross product. And so if C is equal to A cross B, there's the magnitude of C, and the direction is by the right-hand rule. And we talked about this before, but just by way of review, we note that in order to get A to align with B, we have to turn A in this clockwise sense, the way I've drawn A and B now. That means I take my fingers and I curl them in the direction of that rotation, and my thumb will point in the direction of C. So C will be into the page, or the circle with an X in it, which denotes an arrow that's flying away from you. A couple of general things that I perhaps neglected to mention in the previous video is that the cross product is perpendicular to both A and B. A and B define a plane, and C is perpendicular to that plane. So one thing that you can take heart in is you will always know with at least a 50-50 what the direction of the cross product between any two vectors is. You just define the plane that is in which the two vectors lie, and you know that the cross product must be perpendicular to that plane. And then you need to use the right-hand rule to determine which direction it is with respect to that plane. All right. So one final thing also is to note, and this is again something which you might have inferred from the previous discussion, but not gotten directly, is that B cross A. If I do B cross A, it's going to have the same magnitude, right? It'll be AB sine theta, or BA sine theta, take your pick. But if I note that B is my first one, I need to align. I need to go clockwise or counterclockwise with B to get it to align with A. So remember, it's always the first vector of the product that matters, whose direction of rotation you need to think about. And then as B rotates towards A, my fingers follow that rotation and my thumb points out. That's outward. So A cross B was inward. B cross A is outward. That's an arrow looking right at you, as it were. So pointing at you. So B cross A is outward, A cross B is inward. This means that A cross B is equal to minus B cross A. Fundamental fact of the cross products. Okay, so much for that. That's more or less review of what we previously did. Now, let's move on and say, all right, what's going to happen now if I have, and I'll do it in all its three-dimensional glory, a sub x I hat plus a sub y j hat plus a sub z k hat. And I have b as b sub x I hat plus b sub y j hat plus b sub z k hat. And now I want to take the cross product A cross B. Well, it's a bit involved, but I'm going to write it out in this way because it's really kind of there's a lot to be considered here. So I've got three terms in each. I'm going to have a total of 9 that I have to deal with. All right, so let's just take them in turn. I'm going to have ax bx, I cross I. Let's decide which way we're going to go here. All right, let's go ax by. Now I cross j. And finally ax bz, I cross k. And now the rest are similar, starting with ay bx, j cross I. Because a is first, we have to keep the unit vectors in that same ordering. That should make sense to you. We've already seen that the order of the product matters. So I cross j is going to be equal to minus j cross I. So we have to be very careful when we're multiplying these in this way to get the right ordering. Plus ay by, j cross j, plus ay bz, j cross k. Finally, az bx, k cross I, plus az by, k cross j, plus az bz, k cross k. All right, so we've now got all 9 terms. And what we need to do next is going to require us to think about the individual cross products between the various basis vectors, the various unit vectors. So let's consider I cross I. If I take the cross product between a vector and itself, we said this before, the cross product of a vector and itself is 0. So I know that I cross I is going to be 0, I know that j cross j is going to be 0, and I know that k cross k is going to be 0. Because the angle between a vector and itself is 0, and sine of 0 is 0. Okay? What about I cross j? For this, in order to evaluate this visibly, I need to do the following. I think it would be helpful if we said, here's the x-axis, here's the y-axis, and here's the z-axis, pointing up out at you. And we need to recognize that actually, really importantly, this is the proper orientation and not z going down. The Cartesian 3-space orientation here is such that x, if I take I hat and j hat, I need to get k hat out. So k hat also comes out. I cross j equals k. I need to rotate I in the counterclockwise sense to get to line it up with j. And so my thumb points in the direction of k. That's how we know we have what's called a right-handed coordinate system. Okay, so I cross j is equal to k. That's by definition. All right? So this gets a little tricky to visualize, but I would say stick with it and watch this video again and again, because it will be helpful for you in the end. You really need to be able to make all of these manipulations with your right hand almost in your sleep. What about I cross k? You can hit pause and figure it out, because I'm going to tell you real quick here. I cross k, I need to take I, and I need to turn it into the direction of k, which means it needs to rotate from here to here. I cross k. The only way for me to get my fingers to circle in that way is to have my thumb pointing down along the y-axis, if you will. Okay? Again, I'm aligning I, turning it to align with k. So that's a rotation in this sense. To get my fingers to rotate in that sense, my thumb needs to point down in this direction. Okay? So this is minus j hat. Now, the next couple are fast. J cross I. We know that I cross j is k hat, so the j cross I has to be minus k hat. And we know that I cross k is minus j hat. That means that k cross I has to be plus j hat. And again, you can do this, you can figure this out. Here's k. Turn k so that it aligns with I. That's that kind of rotation, which means my thumb points up the y-axis. Okay? All right, last one is going to be j cross k. What about j cross k? Here's j. J is turning so that it comes to align with k. In order to do that, my fingers have to, in order for my fingers to make that same sense of rotation, my thumb points out the x-axis, so this is positive I hat. And then similarly, k cross j will have to be minus I hat. All right, there is my table of basic unit vector cross products, which then allows me to evaluate what's up here, A cross B. All right, so I'm going to do that. I'm going to do that relatively quickly. But again, you can pause and check it out yourself. All of these go to 0. And then the others we can just write down. So let's do that. So we've got A cross B is equal, first term I got AX BY, I cross J is K hat. We got AX BZ. How about I write what I say? AX BZ, IK is minus J hat. AYBX, JI gives me a minus K hat. AYBZ, JK, J cross K gives me I hat. I got then AZBX, K cross I gives me J hat. And finally, AZBY, K cross J gives me minus I hat. All right, we can group these in terms of the I's, J's, and K's. So I've got two I terms, AYBZ minus AZBY times I hat. That takes care of those two. Then I've got plus AZBX minus AXBZ times j hat. And then finally, so those are wiped out. I've got axby minus aybx times k hat. So there is the full expression of the cross product in component notation. You can see it's a vector. Yeah, so there's a slightly simpler way to get that same form. And this is by way of definition. If you are comfortable with matrices, it's going to be helpful. Some of you will be, some of you may not be, and that's okay. You could just do things like this if you like. But I want to show you this because it is handy. So A cross B, it turns out that it is equal to the determinant of a 3 by 3 matrix, where the first row is I hat, j hat, k hat. The second row is the first vector written in component notation, ax, ay, az. And the third row is likewise bx, by, bz. Okay, in order to evaluate this, you need to know how to do a 3 by 3 determinant. Okay? Well, in order to do a 3 by 3 determinant, again, if this is beyond your experience, I will not worry. We have the previous expression to go with. But in order to do this, I need to take that vector I hat, or that part of the 3 by 3 matrix, and multiply by the determinant of the bottom. The other portion, if you like, that is opposite kitty corner this I hat. So I need the determinant of this 2 by 2. Now most of you probably know the determinant of a 2 by 2 matrix is the upper left times the lower right minus the lower left times the upper right, right? So this is I hat times the determinant of this 4 by 4, or 2 by 2. AYBZ minus AZBY. The second term in the determinant takes minus this, so minus j hat, and then I do the determinant formed by the other columns. So these two and these two. So minus j hat times the determinant of this submatrix. AXBZ minus BXAZ, or minus AZBX. And then the last term is given by plus that component times then the determinant of this 2 by 2. AXBY minus BXAY, or AYBX. So this is the same as the expression we previously wrote down. It's just a little bit easier to deal with. Okay? So let me just give one example of doing this work. And that is, let me just work with some unitless vectors. If A is I hat plus 3j hat minus k hat, and B is 4I hat plus j hat plus 3k hat, then we can find A cross B as the determinant of this 3 by 3 matrix, I, j, k, 1, 3, minus 1, and 4, 1, 3. So I'll do that. I get I times 3 minus 1 times minus 1. So 3 times 3 minus 1 times minus 1. I'm writing it all out completely. Then minus j times this determinant, this guy and that guy. So 1 times 3 minus 4 times minus 1. And then plus k hat times the determinant of this pair down here. 1 times 1 minus 4 times 3. All right, this turns out then to be 9 plus 1 is 10 I hat. This is 3 plus 4, but then the minus sign, so minus 7 j hat. And then this is 1 minus 12, or minus 11 k hat. That would be my cross product of A and B. All right, long-winded stuff, really important, will be really helpful for us as we consider torques later in the semester, which are given by cross products. I hope this was clear as mud, and we'll see you next time for a slightly different topic. Will take us outside of the vectors and into a little bit of calculus.